Okay, good morning. Today we finish off on the Maclaurin series. So we said the Maclaurin series is a power series, and it is one way to rewrite a seemingly complicated function into something easier, because all our coefficients are you can rewrite them in a better way. Anyway, that's what I mean, right? So we rewrote some functions like sine x. We said it's a power series because you have ascending powers of x, so the powers of x are increasing. You start with x to the power of 0, x to the power of 1, x to the power of 2, and so on. So it's a series, that means it never ends. And you can actually use it to approximate values of functions. And I think some calculators even use this method. Like if you say what is square root of x, you can work this out by rewriting square root of x as a power series, and then you substitute x. Then depending on the accuracy that you're looking for, then you decide on the number of terms that you want into your series. So the more terms you have, the more accurate your result. The fewer your terms, then the less accurate your result will be. So let's look at some more examples of the Maclaurin series. Let's say my function is y is equal to the square root of 1 plus x. So I want to rewrite this as a power series, the Maclaurin series. Now remember what we need. First, we will substitute 0 into the function. So we have y of 0. This is just the square root of 1, which is equal to 1. And then you find the derivative. So here you can see that rewriting a function as a Maclaurin series is one of the applications of differentiation. So I find the first derivative, y prime. This is equal to, the half will come down, the inside will stay as it is, and then the exponent will decrease by 1. So I have half minus 1, which is minus a half. And then I substitute 0 in there, so I have y prime of 0. This is equal to a half, because inside my bracket I'll have 1 plus 0, which is just equal to 1, and 1 to the power of anything is just equal to 1. And then I find the second derivative, y prime, y double prime. Now the derivative of the inside is equal to 1, so even if I don't mention it, I am multiplying by the derivative of the inside. So I'm using the chain rule. You differentiate the outside, and then the inside, you multiply them. But the derivative of the inside, this 1 plus x, is just equal to 1. So multiplying by 1 is the same as not doing anything. So y double prime, this time the negative half will come down, and then I'll multiply it with the half. So I have negative 1/4, and I have 1 plus x. The inside will stay as it is. The exponent will decrease by 1. So I have minus a half minus 1. So this is minus 3 over 2. When you multiply by the derivative of the inside, you get times 1, but multiplying by 1 doesn't change anything. Then again, you substitute 0 into the second derivative, and this time you get 1 over 4. Then you can work out the third derivative. So y triple prime, this is just the derivative of the second derivative. So the negative 3 over 2, this exponent, will come down. Now when it comes down, it multiplies with the negative 1/4, which is there. Negative and negative, this will be positive. So I have 3 over 8. And then the inside will stay as it is. The exponent will decrease by 1. So I have negative 5 over 2. And then I'll multiply with the derivative of the inside, which is multiplying by 1. but multiplying by 1 doesn't change anything. Then I substitute y double prime of 0. I substitute 0 into y triple prime, then I get 3/8. Okay, so I think I have enough terms now to rewrite this as the Maclaurin series. So remember your f of x or your y, use y here. So you have y, this is just y of 0 plus y prime of 0, then x over 1 factorial, and then you add y double prime of 0 times x squared divided by 2 factorial, and then you have y triple prime of 0, x to the power of 3 divided by 3 factorial, and then you continue in that manner. So a series never ends, it just continues like that. So depending on the number of terms that you're asked to find, then you will decide where to stop. Then, now that I have the formula for the Maclaurin series, all I do is substitute. So I worked this out. My value was 1. I worked that one out. I got half. This was minus a quarter, and this was 3/8. So I just substitute them. So my y, this was square root of 1 plus x. And this is equal to y of 0, we say it is 1. And then I add y prime of 0, which is half. And then I multiplied by x to the power of 1 divided by 1 factorial, but 1 factorial is just equal to 1. And then y double prime of 0, this is minus 1/4. Then I multiply this by x to the power of 2 and divide this by 2 factorial. And then the last term that I have here, this is 3/8, which is y triple prime of 0. And then you multiply this by x to the power of 3 over 3 factorial. And I put plus and my dots to show that this continues, it doesn't just stop over there. So when I rewrite this nicely, I have 1 plus half x minus 1/4 multiplied by 2 factorial. That's the same as 1/4 times half, which is 1/8. And then I'm multiplying this by x squared, so this will be x squared over 2. And then the next term I have this 3/8 times 1/3 factorial. The 3 and the 3 factorial will cancel. I'll be left with 2 factorial. 2 factorial is equal to 2, so I have 8 times 2. So this is 1/16 times x cubed. So this is just x cubed over 16, and then I put my dots over there. So now if I can actually use this to work out the square root of anything. Now if, for example, I want to work out the square root of 2, I know this is equal to 1 plus 1. So my x in this case is, this is my x, this is 1. So I'm looking at this function that I have, it's 1 plus something. So if I wanted to work out square root of 2, I can approximate it. This is 1 plus half times 1 minus 1 squared over 8 plus 1 cubed over 16. So if we do that on our calculators, we have 1 plus a half minus 1/8 plus 1/16, and this gives me 1.4375. Now the actual value of square root of 2, this is equal to 1.414213, and it continues. So you can see this is a pretty close approximation, and I only have 4 terms. So the more terms I have, you will notice that this gets closer and closer to the actual value of square root of 2. So that's one of the reasons why we rewrite functions as Maclaurin series, because with Maclaurin series, even without a calculator, I can work out what square root of 2 is with a pretty good approximation. Now let's look at another example. Let's say we have y is equal to sec x. So I want to rewrite this as a Maclaurin series. First, we find out what y of 0 is. Y of 0, this is equal to 1 because sec of 0 is equal to 1. Sec of x, this is 1 over cos x. So 1 over cos of 0 is just equal to 1. Then I find the first derivative as usual. So y prime. So I differentiate sec x. When I differentiate sec x, I get sec x and tan x. Okay, this one you can read from your table. And then I substitute 0 into the first derivative. This will give me 0 because tan of 0 is 0. So whatever the value of sec x is, when I multiply it by tan of 0, my answer will be 0. Then the second derivative, to work this one out, what I need to do is use the product rule. So I will differentiate sec x and multiply that by tan x, and then sec x multiplied by the derivative of tan x. So when I do that, I say keep sec x constant, the derivative of tan x, this is sec squared x. Then I'm going to add this to the derivative of sec x, which is sec x tan x, and then I multiply this by tan x. Okay, then I simplify this, and what I get is sec cubed of x plus sec x tan squared x. Now I know that I will have to differentiate this again, so what I will do is I will rewrite this tan squared x in terms of sec x, because I don't want to use the product rule, because it can get very tedious when you use the product rule. So what I have, this is sec cubed x plus sec x, and then tan x, this is the same as sec squared x minus 1. Okay, so that's what we have. Then can multiply out, and then what we have is sec cubed x plus sec cubed x minus sec x. And you can see that these two can combine. This is 2 sec cubed x minus sec x. All right, then we substitute 0 into that formula. You get y double prime of 0. This is equal to 2 times 1, because sec of 0 is 1. When I cube that, I get 1, and then I have minus 1. So this is 2 minus 1, and then I get 1. So this is y double prime. Then I work out y triple prime. So y triple prime, I'm going to differentiate the second derivative. So here, when I differentiate it, this 3 will come down and multiply with the 2. So I get 6 sec squared x. The exponent of sec x has decreased. And then the derivative of the inside, the derivative of sec x. Just a moment. Then the derivative of sec x, you're inside, this is sec x tan x. Okay, that's an x over there. Right, then the second one, this is minus the derivative of sec x, which is just sec x tan x. Okay, so we simplify what we have here. I have sec x times sec x. This is 6 sec cubed of x tan x, and then minus sec x tan x. Right, then I will substitute 0 into the third derivative. Y triple prime of 0. This is just going to be 0 because tan of 0 is 0. So what I have is 0 minus 0, which is equal to 0. So now to get the fourth derivative, I can't really change the sec that I have here. So the sec cubed and the sec over there in terms of tan. So here I have no choice but to use the product rule. So the fourth derivative, I will keep 6 sec cubed x as it is, and then multiply it by the derivative of tan x, which is sec squared x, and then I will add this to the derivative of 6 sec cubed x, which will be 18 sec squared x, multiplied by the derivative of sec x, which is sec x tan x, and then now I will multiply with tan x. So this is times tan x. Okay, so here I was differentiating this part. So this is the derivative of 6 sec cubed x. The 3 comes down, multiplies with the 6, you get 18. The exponent of sec decreases by 1. Then the derivative of the inside, which is sec x, is sec x tan x. And then you multiply by tan x. So I've differentiated the first term. Then I have to differentiate the second one, also using the product rule. So now I'm differentiating this over here. Okay, and notice it is minus, so everything will be negative. So I have negative. First, sec x will remain as it is, and then I multiply by the derivative of tan x, which is sec squared x. And then instead of plus, I put minus because the negative over here multiplies with the plus that comes from the product rule. And then I have sec tan x will stay as it is, and then I will multiply by the derivative of sec x, which is sec x tan x, like that. So we can simplify this and see what we get. So for the first one, I have 6 sec to the power of 5 of x, and then plus 18 sec to the power of 3 of x, and then this is multiplying by 10 to the power of 2 of x, and then minus sec to the power of 3 of x, and then minus 10 to the power of 2 of x, and then sec x. Okay, so here you will notice that I have tan in the second term because it's a product, and I also have tan over there. So when I substitute 0 over there, I will get 0 because tan of 0 is 0. So when I work out y of, sorry, this is the fourth derivative of 0, what I get is 6 times 1 because sec of 0 is equal to 1, and then 1 to the power 5 is just 1. The second term is 0. Then the third term, I get minus sec of 0, which is 1. 1 cubed is just 1. And then the last term is 0. So this leaves me with 5. Okay, so I think I have 3 terms that I can write. The first one was 1. The second one is 0. The third one is 0. The fourth one, which I have now, this is 5. So I think I have enough terms to rewrite this. So I can say that sec x, this is equal to 1. Then the second term was 0. I would multiply it by x, but since I'm multiplying by 0, there's no need for me to write it. And then the second one, I had x. Sorry, not x. I had 1 as well. Then I multiply this by x squared over 2 factorial. And then I had 0. And then the last one, I had 5x to the power of 4 divided by 4 factorial, and then I put the dots there to show that it continues. So this is equal to 1 plus x squared over 2 factorial plus 5x to the power of 4 over 4 factorial, and it continues in this manner. Okay, so we're rewriting a function as a Maclaurin series isn't difficult. It's just tedious because the derivatives, like you can see over here, the derivatives that I'm getting keep getting bigger and bigger. So the more terms you want, the more tedious the work, but there isn't anything difficult that I am doing. Right, then let's look at one more. If we have y is equal to sine of pi over 4 plus x. Now to work out this as a Maclaurin series, I will first substitute 0 in there. This is equal to sine of pi over 4 because x is 0. So sine of pi over 4, this is just square root of 2 over 2. Then again, I differentiate y prime. On the outside, I have sine, so the derivative of sine, this is cos. The inside must stay the way it is. And then I multiply by the derivative of the inside. The derivative of the inside, I have pi over 4, the derivative is 0. X, the derivative is 1. Then I have 0 plus 1, which is 1. So I will be multiplying by 1, and we know that multiplying by 1 doesn't change anything. So that is the first derivative. Then I substitute 0 into the first derivative. I will end up with cos pi over 4. This is just equal to the square root of 2 over 2. Then I find my second derivative. On the outside I have cos, so the derivative of cos is minus sine. The inside must stay the way it is. And then the derivative of the inside is 1, so this is my second derivative. So y double prime of 0, this is minus sine of pi over 4, which is just minus square root of 2 over 2. Then I want one more term, so I will work out the third derivative. Here I'm differentiating minus sine of pi over 4 plus x, so the minus will remain there and multiply by the derivative of sine of x. The derivative of sine is cos. The inside must stay the way it is. And then you multiply by the derivative of the inside, which is equal to 1. So it doesn't change anything. Then I find y triple prime of 0. This is also equal to minus square root of 2 over 2. Okay, so I think 4 terms is a good enough approximation. So now I rewrite it according to the Maclaurin series formula. So sine of pi pi over 4 plus x, and this is equal to y of 0, which is square root of 2 over 2, and then I add the next one, y prime of 0, this is square root of 2 over 2, then you multiply this by x, and the next one was negative square root of 2 over 2, you have x squared, this is multiplying, divided by 2 factorial, and then the next was negative, so it was negative square root of 2 over 2 multiplied by x to the power of 3 over 3 factorial, and then plus dot 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 to show that it continues. So we can simplify this just a little bit. So we have square root of 2 over 2 plus square root of 2 over 2x minus square root of 2 x cubed divided by 4. If you want to, you can rewrite square root of 2 over 2. We rewrite 4 as square root of 2 to the power of 4. Yeah, and then cancel some of the square roots if you like, but even this is fine. Then I have minus square root of 2 x to the power of 3. Then 3 factorial is 6 times 2 is 12. And then it continues in this manner. So if I wanted to work out sec of 0, for example, this means that, sorry, not sec of 0, if I wanted to work out sec of pi over 4 using this formula, it means my x should be equal to 0. Then you'll notice that all these terms here, they have an x, so they'll disappear. And sec of, is this sec? No, sine. Sorry, I'm looking at the wrong function. This was sine. I write sec over here. No, that's sine. Okay, so sine of pi over 4 is just equal to square root of 2 over 2. And I can also work out sine of pi using this same formula. So if I want to work out sine of pi, I know that sine of pi, this is just equal to sine of pi over 4 plus 3 pi over 4. So this value here, this is my x in the equation. So here I'll substitute x, I'll substitute x, I'll substitute x, and then that will give me an approximation of what sine pi is. Now we know what sine pi is because it's one of the special angles, but you can also check using the Maclaurin series. You will get the same answer. So that's basically it on the Maclaurin series. It's one of the applications of differentiation, that if you know how to differentiate, you can write almost any function as a power series. There are some that you cannot rewrite as a power series. For example, y is equal to x. After you differentiate, the derivatives disappear, so you cannot write that as a power series. But functions that have an infinite number of derivatives, that means you can keep differentiating without the function ever disappearing, or without the denominator being 0, you can rewrite them as a power series. For example, 1 over x, that one you cannot rewrite it as a Maclaurin series, because when you substitute the 0, you'll have 1 over 0. So what I'm saying is this: if you have y is equal to 1 over x, you cannot rewrite this one as a Maclaurin series, because with every derivative, x is in the denominator, and when you substitute 0 in there, what you have is undefined, even though it has an infinite number of derivatives. That means you can just keep on differentiating, you will get a function, but because of the fact that when you substitute 0 into the function and its derivatives, what you have is undefined, you cannot rewrite it as a Maclaurin series. Okay, the same for y is equal to 1 over x squared, something like that. But y is equal to 1 over x plus 1. I believe we did something like that. That one you can rewrite it as a Maclaurin series. Okay, so that's basically it again. So nothing too complicated. You just need to know how to differentiate. And the best way to get the hang of differentiation is really just to practice. There are more exercises in your notes that you can look at. Some of those derivatives are quite tedious, but again, not difficult. I haven't seen one that looks or that is difficult. It's just that it takes a while to differentiate it. And the more terms you are looking for, the more derivatives you will have to get. So I just want to introduce integration. We won't go into much detail, but just to introduce integration. Now integration, this is the inverse function of differentiation. Now remember with differentiation, what we're looking for is the slope. So we're trying to get the slope or the gradient. And what the slope of the gradient tells us, if I have a function, we're saying how is the function changing? How are the values of y? So it's delta y over delta x. When how is y changing when x is changing? That's what we're looking for with our gradient or the slope. So we gave practical examples that if you have the displacement and then you differentiate this, you can differentiate ds dt, you get your velocity, and then when you differentiate that dv dt, here you get your acceleration. Okay, so how fast is the displacement changing with respect to time gives you the velocity. How fast is the velocity changing with respect to time? That gives you the acceleration. Then with integration, we will be going in the opposite direction. So let's say I give you the acceleration. So I tell you the velocity is changing at this rate. Can you tell me what the velocity is? So from the acceleration, we will then work out the velocity. And then if I give you the velocity, are you able to tell me what the displacement is? Okay, so it's like going backwards now. So we started with our displacement. We differentiate to get the velocity, we differentiate that to get acceleration. Now we'll be working backwards. I say, here is the acceleration. Can you tell me what the velocity is? And then here's the velocity. Can you tell me what the displacement is? Now there are two types of integrals that we will work out. So with integration, we use this symbol. This is a symbol for integration. And we are saying we integrate a function f of x with respect to x. So this dx tells me what variable I am integrating with respect to. So this means integrate with respect to x. Okay, so this f of x, this is your gradient. That is what you got after you differentiated. Now when I ask you what is the integral of f of x dx, what I'm asking you to do is give me a function g of x such that g prime of x, this is equal to f of x. So I tell you, give me a function that when I differentiate it, this is the answer. Okay. So for example, if I gave you this and I said integrate x with respect to x, or the integral of x dx, your answer, let's say h of x, could, for example, be x squared over 2. Because if I differentiate h of x, so I find h prime of x, this is equal to 2x power 1 over 2. This is just equal to x. So when I differentiate my h of x, I get this function that I have over there. So that is why I can write, say here, I can say that the integral of x with respect to x is equal to x squared over 2. So that's one of the solutions, because when I differentiate this function here, I do get x. So I'm giving you the gradient, I'm giving you the slope, and you have to tell me the function that I differentiated in order to get that slope. Now, I mentioned the definite integral, or maybe not. What I'm doing over here, when I say d of f of x dx, this is what we call the indefinite integral. Okay, now the indefinite integral, what you get from evaluating the indefinite integral is a family of curves that satisfy the integral. So what that means is this function, when I integrated it, I said the answer is x squared over 2. And that is correct, because when I differentiate x squared over 2, my answer is x. But somebody else could say, but if I differentiate x squared over 2 plus 5, I also get x, isn't it? So if I were to differentiate this, this is still equal to x. The 2 will come down and cancel with the 2 in the denominator, and then the derivative of 5 is equal to 0. So I'll have x plus 0, which is equal to x. And another person will say, even if I have this plus pi, the derivative of that is also equal to x. And another person could come up with something like that. The derivative is also equal to x, and they are all correct. Now with the indefinite integral, you can see there's something common with all our integrals. The part that they have in common is this over here, the x squared over 2. All of them have x squared over 2. Even the first one that I did, it had x squared over 2. Now what they differ by is this term here, this 5 pi e to the power of pi. So they differ by a constant. Okay, so when we have to find the the indefinite integral, our solution is not a single curve, because if I say this is my solution, it means that's the only one that I can differentiate to get x. But we're saying that when we're taking the definite integral of x with respect to x, our solution should be x squared over 2, and then I add a constant c. Okay, now this constant represents whether it's your 5, your pi, your e to the power of pi, it doesn't matter. So it's some constant, because when I differentiate this function now, the constant derivative will be equal to 0, and I will still end up with x like I did over there. So when we have this, an indefinite integral, we must always have a constant just to represent the cases where you have terms that when you differentiated them, they ended up as 0. Okay, so this is the indefinite integral. So your solution is a family of curves. So the C represents whatever constant you put there. So it's not just one answer. There are several. Some person will put 1, another person will put 10, somebody else will put 100, another person will put sign of 50, and so on. So it's not just one solution. There is more than one. Then there is the definite integral, which we will also talk about a little bit later, but first we look at some of the techniques that we use with integration. Now, with the indefinite integral, there are some rules of integration. The first one is that if you integrate a constant multiplied by a function with respect to x, what you can do is you can take the constant out and then integrate your function and then multiply that by the k. So this is the same as k multiplied by the integral of f of x dx. Okay, so this one you can work it out and then multiply your answer with k. So just like we were doing with differentiation, when we had a constant that was multiplying your function, like when I had 2 sine x, and then I say differentiate this, you can take the 2 out, differentiate your sine x, you get 2, the derivative of sine x, this is cos x, and then finally leave your answer as cos x. So the same rule applies over here. So this is by the way. And then another one, that is the first one, where you have a constant. So a constant doesn't mean x. So if I have x times sine x, I cannot take the x out and then integrate sine x. I cannot do that. So it must be a constant, an expression that has no x in it. Then the next one is the sum and the difference rule, that if you are integrating the sum or a difference of two functions of x with respect to x, what you can do is just integrate the first one with respect to x and then add or subtract the integral of the second one also with respect to x. And we know we did this when we were looking at derivatives. So if I gave you something like this, sine x plus cos x, and then I say differentiate this one, you differentiated sine x, and then you differentiated cos x. So you say this is cos x minus sine x. So you differentiate each of them and then you add them together. So the same rule also applies here when we are talking about integrals. And then there are some standard integrals. So this is like a table with the one we used when we were differentiating. So these are some standard integrals. So you can use these when you are integrating, just like we did with the integration, with the differentiation table. So you always have to keep in mind what we are doing with integration. I'm looking for a function that when I differentiate it, it must be equal to the function that I integrated. So the first one, the integral of a dx. So here I am integrating a constant. So when I integrate a constant, this is what I get. I get ax plus c. So it doesn't matter what your constant is. So here, this makes sense because my gradient, if my gradient is a number, it means my graph is a straight line, because a straight line is the function that has a constant gradient. At every point on your straight line, the gradient is the same. Remember, this is our gradient. And then this is the curve which has this as the gradient. So I give you the gradient and then I ask you what is the function. So this ax plus c, that is the equation of a straight line. Okay, so if your gradient is constant, it means that your curve is a straight line. Okay, and c is any constant here, because when I differentiate ax plus c, we can try that. Let's differentiate it. we have ax plus c. We differentiate this. This is the derivative of ax. This is just equal to a. The derivative of c, this is 0. And this is just a, which is what I was doing there. So when I ask you to integrate, I'm saying give me a function that when I differentiate it, the answer is equal to the function that I gave you. That's what integration means. And the next one we look at is the integral of x to the power of n dx. Now this one, remember that integrals and derivatives are opposite functions. Now when I gave you a function to differentiate, let's say x to the power of n, let me write this in grade. When I gave you a function x to the power of n, and then I said differentiate this, remember the procedure, the n will come down, and then at the exponent I will decrease by 1. So here we will do the opposite of bringing the n down, and then when I bring the n down, what I was doing is multiplying. Okay, so I multiply by the n and then decrease by 1. So the opposite of that means I must now add 1, and then I must now divide by this. That is the opposite of multiplying by n and then subtracting n at the top, sorry. So here on our table, you will see that if you want to integrate x to the power of n, and this is an indefinite integral, what you should get is x to the power of n plus 1 divided by n plus 1, and then you must always add your constant c. So that is for the function that becomes 0. Okay, so c represents whatever becomes 0 after you differentiate it. So that is how we get that one, and I used it with the first example I gave you when I said the integral of x dx. So here, when you would do it, this is x to the power of, this is 1, so I get x to the power of 2. Let me just say it's 1 plus 1, and then I divide by 1 plus 1 plus c. And this is just equal to x to the power of 2 over 2 plus c. So I used it even without saying, and that is actually how I got the derivative of x. Sorry, the integral of x dx is x squared over 2 plus c. Can look at some more. Let's say I have x cubed dx. If I want to find this indefinite integral, this is just x to the power of 4 over 4 plus c, and just like that. So you add 1 to your exponent, and then you divide by that same exponent. And you'll see when you differentiate this, this 4 comes down to multiply. It'll cancel with this one that is dividing, and then at the exponent I will be left with 3. Then the next integral we have is the integral of 1 over x dx. The integral of 1 over x dx is just ln of x plus c. Now remember, when we were differentiating ln of x, our answer was 1 over x. So now if I tell you the gradient is 1 over x, then it means that the function I differentiated to get 1 over x must be ln of x. Then we have the integral of e to the power of x dx. This is just e to the power of x plus c, because when I differentiate this, my answer is just e to the power of x. Then this is number 7. I have the integral of ax excuse me, dx. This is equal to 1 over ln of a to the power of x plus c. Now here A must be positive, okay, because you cannot take ln of a negative number. And here A is not equal to 1. So it is not equal to 1 because if it is equal to 1, then our denominator is equal to 0. And if A is negative, you are taking a logarithm of a negative term, which you are not allowed to do. So number 8, we have the integral of cos x dx. This is just equal to sine x plus c, because when I differentiate sine x plus c, my answer is cos x. Then number 9, the integral of sine x dx. This one here is negative cos x plus c, because when I differentiate cos x, I get negative sine. And then when I multiply it with this negative, then I will have positive cos x. Right, so there are more examples or more standard integrals on the table. So number 10, which is the integral of sec squared. So we know that when we differentiate 10, we get sec squared. So when I integrate sec squared, I should end up with 10. And cosec squared, when I differentiate cot x, I get negative cosec squared. So the integral of cosec squared is negative cot, and so on. So you look at this table, it's like we're reversing the derivatives with the integrals. So we're now on the right hand side of the derivative table and integrating those ones. So we will continue on Monday. We look at some more examples of how to differentiate, how to integrate. Okay, so have a good weekend. Please get ready for the test on Wednesday, and I'll see you guys on Monday.